There is a smudge of light in the southern sky that has been there since before recorded history, and for most of that time, no one had any idea what they were looking at. To the naked eye, it looks almost like a star that cannot quite focus. Soft at the edges, slightly too wide, ancient astronomers catalogued it and moved on. What they were actually looking at was 10 million suns packed into a sphere 150 light years across, close enough to see without a telescope, and strange enough that modern astronomers are still arguing about what it really is. That number, 10 million stars, does not process correctly the first time you hear it. Our nearest stellar neighbour is 4.25 light years away. Inside this object, the average distance between any two stars is 1/10 of a light year. The stars are so tightly packed that some of them collide, some of them steal material from each other, some of them produce objects that have no business existing. For centuries, astronomers called it a globular cluster and thought that was enough. It is not enough. This thing is 10 times more massive than any normal cluster in the galaxy. It rotates differently. It is shaped differently. It has a trail of stripped stars stretching 18 degrees across the sky, and sitting somewhere at its center is something scientists spent decades arguing about. Something that finally forced them to rethink what this object is entirely. Tonight, you will understand what you are actually looking at when you find that smudge above the southern horizon. Now look south. We begin. To understand what Omega Centauri actually is, you have to start with a number that your brain is not going to process correctly the first time you hear it: 10 million stars. Not 10 million points of light scattered across a wide swath of sky, but 10 million stars packed into a single gravitationally bound sphere, orbiting the Milky Way together as one object. That number is the starting point, and almost everything strange about this system follows from it. Start with what a globular cluster actually is. The Milky Way has roughly 200 of them, ancient collections of stars held together by their own gravity. Orbiting the galaxy the way a moon orbits a planet, they are some of the oldest structures in the universe. Most of them contain anywhere from tens of thousands to a few 100,000 stars. They are roughly spherical. They are dense toward the center, and they thin out gradually toward the edges. That is the standard definition. A globular cluster is a gravitational city, stars that form together and have stayed together for billions of years, slowly circling the galaxy in a long looping orbit. Omega Centauri fits that definition. It is gravitationally bound. It orbits the Milky Way. It is spherical, or close to it. But the moment you put actual numbers to it, it stops behaving like anything else in its category. The Milky Way's average large globular cluster might hold 300,000 stars. Omega Centauri holds 10 million. It is roughly 10 times more massive than the next largest globular cluster in our galaxy. It spans about 150 light years from edge to edge. That sounds abstract, until you remember that the distance from our Sun to its nearest stellar neighbor is just over 4 light years. Omega Centauri contains enough stars to fill that kind of space 150 times over, and they are not spread thin. They are packed in. The total mass of the cluster is somewhere around 4 million times the mass of our Sun. It is the largest, most massive globular cluster in the entire Milky Way, and it is not close. Nothing else in our galaxy's collection comes near it. The second brightest globular cluster visible from Earth, a cluster called 47 Tucanae, is impressive by almost any measure. Against Omega Centauri, it looks like a footnote. Now consider where this object is sitting. Omega Centauri is approximately 17,000 light-years. Approximately 17,000 light-years is an almost meaningless distance. The light arriving at your eyes tonight left the cluster 17,000 years ago, when the last ice age was still reshaping the northern continents. And yet, from a dark location in the southern hemisphere, Omega Centauri appears nearly as large as the full moon on the sky. It has an apparent diameter of about 36 arc-minutes. The full moon is about 30 arc-minutes. So this object, sitting 17,000 light-years away, covers a patch of sky comparable to Earth's nearest natural satellite. That tells you something. An object does not appear that large at that distance by accident. Omega Centauri is pumping out an enormous amount of light. Its apparent magnitude is 3.9, which means it is plainly visible to the naked eye on any clear night from the right latitude. People in the southern half of the United States can see it. Anyone south of roughly 40 degrees north latitude can find it without a telescope or binoculars. For the entire southern hemisphere, it has been a permanent feature of the sky for as long as humans have been looking up. What you see with the naked eye is a smudge, a fuzzy patch that does not resolve into individual points of light. Binoculars begin to hint at the structure. A modest telescope starts to break it apart at the edges. A larger instrument aimed at a dark sky shows something that looks almost like a galaxy, a dense, glowing core surrounded by a halo of individual stars trailing off in every direction. The visual effect is striking enough that observers have been noting it for centuries without fully understanding what they were seeing. And what they were seeing is this: a sphere of 10 million suns, most of them old, most of them yellow or red or cooling toward white, all of them gravitationally locked to each other, orbiting the Milky Way on a path that swings above and below the galactic plane on a cycle of roughly 120 million years. From the outside, it is one of the most spectacular objects in the southern sky. From the inside, it would be something else entirely, but that comes later. The category it officially belongs to is globular cluster. That is the label astronomers applied to it, the drawer it sits in, the classification that determines how it is discussed and compared. For a long time, that classification felt adequate. It has all the surface features. It orbits the galaxy. It is old. It is gravitationally self-contained. Globular cluster. Settled. Then researchers started measuring things more carefully. They measured its mass and found it was in a league of its own. They measured how fast it was rotating and found it spun faster than other clusters. They looked at the chemical composition of its stars and found something that should not have been there. They found stars of different ages, different chemistries, different generations, evidence that star formation inside this object had not happened once, in a single burst, the way it happens in every other globular cluster in the Milky Way. And the more carefully astronomers looked at Omega Centauri, the more that label, globular cluster, started to feel like the wrong answer. If you built a scale model of Omega Centauri's core and tried to represent each star with a grain of sand, you would need roughly 10 million grains packed into a sphere the size of a building. Not a stadium, not a city block. A building. Hold that image for a moment, because the number itself, 10 million stars, tends to slide through the mind without catching on anything. The scale model forces it to land somewhere real. Now consider what that actually means in terms of distance. The cluster's full diameter runs to about 150 light-years. That sounds enormous, and in absolute terms it is. But pack 10 million stars into that space and something strange happens to the math. In the outer regions, the stars are spread reasonably wide. Move toward the center though and they close in fast. In the core of Omega Centauri, the average distance between any two stars is roughly 1/10 of a light-year. That number needs a comparison to mean anything, so here is one. The nearest star to our own Sun is Proxima Centauri, sitting about 4.25 light-years away. The average gap between stars in Omega Centauri's core is roughly 13 times smaller than that, 13 times closer than our closest neighbour. In our solar neighbourhood, the nearest star is so far away that it takes light more than 4 years to reach us. In this cluster's core, the equivalent would be sitting just past Pluto. Let that comparison do its work. Pluto is roughly 40 astronomical units from the Sun. Light takes about 5.5 hours to get there. A star that close to our own Sun would be a fixed, brilliant point in the sky, visible in daylight. Every person on Earth would know its name. In the core of Omega Centauri, that spacing is simply average. It is the ordinary distance between neighbours. To put it in a scale model that stays closer to human experience, imagine shrinking the solar system down so that the distance from the Sun to the Earth equals 1 inch. On that scale, the nearest star to our Sun would sit about 4.5 miles away. On that same scale, the average stellar spacing in Omega Centauri's core would be roughly 1/3 of a mile. Not 4.5 miles of empty space between neighbouring suns, 1/3 of a mile. In that model, you would be able to see the neighbouring stars as distinct objects. You could almost walk to them. This is not a subtle difference. It is a different kind of universe. Our solar neighbourhood is mostly emptiness. Stars are rare points scattered through vast, silent volumes of nothing. Omega Centauri's core is the opposite. Stars crowd together so tightly that the gravitational influence of one bleeds directly into the gravitational influence of the next. There is no clean isolation. Every star in that core is embedded in a web of competing gravitational pulls from dozens of nearby neighbours, all tugging simultaneously, all shifting in relation to each other as the cluster slowly rotates and evolves over billions of years. The cluster's total mass sits around 4 million times the mass of the Sun. That mass is not spread evenly through the 150 light-year diameter. It concentrates toward the centre. The inner core is where the density peaks, and that peak is dramatic. Astronomers estimate roughly 1 star per 1/10 of a cubic light-year in the densest regions. Compare that to our local stellar neighbourhood, where you might find 1 star per 30 or 40 cubic light-years of space. The core of Omega Centauri is hundreds of times denser than the region of the galaxy we call home. What this means in practical terms is that encounters between stars are not rare in this environment. In our part of the galaxy, the stars are so widely separated that close gravitational encounters between two stars are essentially unheard of over the entire lifetime of the galaxy. The distances are simply too great. Omega Centauri's core operates under different rules. Stars pass close enough to each other on regular timescales, astronomically speaking, that their gravity genuinely disturbs one another. Some encounters are gentle, a slight bending of a nearby star's path, a small perturbation in any planets that might be orbiting it. Others are not gentle at all. At close enough separations, two stars begin to strip material from each other's outer layers. One star can pour gas onto its companion, fundamentally altering the companion's chemistry and structure. Under the right conditions, two stars can merge entirely, fusing into a single object that carries the combined mass of both. The result is something that does not fit the standard evolutionary picture. A star born 12 billion years ago should look its age by now. Dim, cool, moving toward the end of its life. But if that old star absorbed a companion somewhere in the past few billion years, it gained a fresh infusion of hydrogen fuel. It starts burning hot and blue again. It looks young. It looks like it does not belong in a cluster this ancient. Astronomers call these objects blue stragglers, and Omega Centauri has them in abundance. Blue stragglers are only possible in dense environments. They are a direct record of the cluster's extreme conditions, written into the spectrum of individual stars. The same conditions that create them also create millisecond pulsars spinning hundreds of times per second, spun up by infalling material from stripped companions, and X-ray binary systems where compact stellar remnants are actively feeding on their neighbours. None of these objects form in isolation. They are products of collision, interaction and theft. They exist because the stars in this cluster are close enough to reach each other. In a space that dense, stars do not just grow old and die quietly. They run into each other, steal material from each other, and occasionally create things that have no business existing. Forget for a moment about the physics. Forget the orbital mechanics and the gravitational dynamics and the stellar velocity dispersions. Just try to picture what it would actually look like to stand somewhere inside Omega Centauri's core and look up. On Earth, a clear night away from city lights gives you roughly 5,000 stars visible to the naked eye. They are spread across the sky in their familiar patterns, isolated points of light, separated by long stretches of darkness. The darkness is actually the dominant feature of our night sky. Most of what you see when you look up is nothing. That is not how it works inside Omega Centauri. In the cluster's core, the sky would be roughly 100 times brighter than the one above your head tonight. Not 100 times more stars scattered through the same darkness, but a fundamentally different kind of sky. A sky where the background glow never drops to black. A sky where the combined light of millions of neighboring suns would be bright enough to cast shadows at what we would call midnight. The darkness that human beings have stared into for all of recorded history simply would not exist there. There would be no night in any sense we recognize. The nearest stars would not look like stars. This is the part that is genuinely strange to try to imagine. Our nearest stellar neighbor, Proxima Centauri, sits 4.25 light-years away. At that distance, it is a point. No telescope you own will show it as anything other than a dot of light. Inside Omega Centauri's core, the average separation between stars is roughly 0.1 light-years. Some neighbors would be sitting at a fraction of that. At those distances, the brightest and largest stars would not be points at all. They would show visible disks. You would be able to see them as objects with actual size, the way we see the moon or Venus through a telescope. Not as pinpricks, but as small glowing spheres hanging in the sky. Some would be close enough that their colour would be obvious without any instrument. Red giants, blue stragglers, yellow sun-like stars, all of them close enough to have a presence, a shape, a weight to them that no star in our sky carries. The sheer number of bright objects overhead would be difficult to separate into individual sources. In certain directions you looked, the stars would blur together into rivers of light. Not the thin band of the Milky Way that we see from Earth, which is itself the combined glow of hundreds of billions of stars spread across 100,000 light-years. This would be tighter than that, more immediate, more overwhelming. You would be looking at 10 million stars packed into a sphere 150 light-years wide, and you would be inside it. The light would be nearly constant. During the equivalent of day, your parent star would rise the way our sun does, but the ambient light from everything surrounding you would mean there was no true transition into darkness when it set. The sky would dim, but it would not go dark. Other stars would fill in the gaps with a collective glow that never fully faded. It would be less like our night sky and more like an overcast afternoon on Earth, except the source of that diffuse light would be the combined output of millions of individual suns in every direction. Then consider what that environment does to any planet trying to exist inside it. Gravitational stability requires predictability. A planet orbits its star in a stable path because the gravitational influence of everything else is weak enough to be ignored over reasonable timescales. In Omega Centauri's core, that assumption collapses. Stars are passing close enough, frequently enough, that their gravity would tug on any orbiting planet continuously. Over millions of years, those accumulated tugs would shift an orbit. Over tens of millions of years, they could eject a planet from its star entirely, sending it tumbling off into the cluster as a dark, frozen wanderer with no sun to orbit. This is why astronomers are fairly confident that the core of Omega Centauri, for all its light and heat and seemingly infinite supply of stellar energy, is almost certainly lifeless. The gravitational interference from neighbouring stars is relentless. Planets that manage to form at all would face an ongoing assault on their orbital stability, accumulating small perturbations that grow into large ones over astronomical timescales. The window for a planet to form, remain stable, and allow the billions of years of relative calm that seem to be required for complex life to develop, is almost certainly too narrow to open in an environment like this. You need a star with room around it, insulated from its neighbours by enough distance that their gravity becomes background noise. In Omega Centaur, eyes, core, nothing is background noise. Everything is close. Everything pulls. The oldest stars in the cluster also formed when the universe had barely begun building up heavier elements: rock, iron, silicon, carbon in solid form. All the ingredients that go into building terrestrial planets were scarcer then. The raw material for Earth-like worlds was simply less available in the early generations. So the picture you are left with is this: a sky so brilliant it never goes fully dark, stars close enough to show their shapes, constant light in every direction from every angle, and almost certainly no one living underneath any of it. The most star-saturated sky imaginable, and almost certainly the least hospitable place in the galaxy to find anyone looking up at it. The object that would eventually be called Omega Centauri had been visible to human eyes for thousands of years before anyone had any idea what it was. It hung in the southern sky, steady and faintly smudged, bright enough to notice, but not bright enough to demand explanation. For most of human history, it was simply there, a fixture in the sky above Africa, above the Mediterranean, above every civilization that ever built cities in the southern world, and no one who looked at it understood what they were seeing. Around 150 AD, the Greco-Roman astronomer Ptolemy catalogued it in his Almagest. He called it a star. More specifically, he described it as a star on the centaur's back, giving it a precise positional designation within his star catalogue. This was not a mistake exactly. It was the limit of what naked-eye astronomy could reveal. To an unaided human eye, even a sharp and careful one, Omega Centauri does not announce itself as a collection of 10 million suns. It appears as a slightly soft point of light, different from a sharp stellar pinprick, but not dramatically so. Ptolemy saw what any careful observer without a telescope could see, and he recorded it faithfully. The catalogue entry would stand unchallenged for more than 5 centuries. Then instruments changed what was possible. In 1677, Edmund Halley, the same astronomer who would later calculate the orbit of the comet that bears his name, was observing from the island of St. Helena in the South Atlantic when he turned his telescope toward this part of the sky. What he saw was not a star, it was a fuzzy patch of light, extended and nebulous, clearly not a point source. Halley catalogued it as a nebula, which at the time was essentially a catch-all term for anything in the sky that did not resolve into a sharp point. He had no way of knowing what it was. He only knew it was not what Ptolemy had written down. This was progress of a specific kind, not an answer, but the recognition that the previous answer was wrong. The object accumulated catalogue entries through the 1700s as European astronomers built increasingly thorough surveys of the southern sky. Swiss astronomer Jean-Philippe de Chazeau included it in his 1746 list of nebulae. French astronomer Lacaille added it to his own catalogue in 1755, and that entry gave it the designation that led eventually to the name Omega Centauri being formally attached to it. Each of these observers was doing the same thing Halley had done, seeing something extended and diffuse, recognizing it was not a point source, and placing it in the general category of blurry celestial objects. None of them could resolve what was inside. Their instruments were good enough to see that something was there, but not good enough to tell them what. The real break came in 1826. Scottish astronomer James Dunlop turned a significantly more powerful telescope on the southern sky from Parramatta in New South Wales and pointed it at this object. What he saw stopped him. He described it as a beautiful globe of stars, very gradually and moderately compressed to the centre. That phrase matters. Not a smear of light, not a nebula, a globe, stars. He could see individual suns. For the first time in recorded history, a human being understood Omega Centauri as a resolved collection of actual stars rather than a formless glow. Dunlop had crossed a threshold that no previous observer had reached, and he described what he found with a precision that still reads as accurate today. This moment set the template for every reclassification that would follow. The object had been a star, then a nebula, then a globe of stars. Each step required better instruments and the willingness to discard the previous answer. The pattern did not stop with Dunlop. As the 19th century gave way to the 20th, spectroscopic analysis revealed that Omega Centauri's stars had chemical compositions different from stars in the Milky Way's disk. Photographic surveys began mapping its structure in finer detail, revealing the concentration of stars toward its core and the gradual thinning at its edges. By the early 20th century, astronomers had firmly established it as a globular cluster, a gravitationally bound sphere of ancient stars orbiting the galaxy as a unit. That classification felt complete. It felt final. It was not final. In the latter half of the 20th century, instruments capable of measuring the velocities and chemical abundances of individual stars inside the cluster began producing results that did not fit. Stars in a normal globular cluster are supposed to share roughly the same chemical composition because they formed from the same cloud of gas in a single burst of star formation. Omega Centauri stars showed a wide range of compositions. Some were extremely metal-poor, consistent with the oldest stars in the universe. Others were relatively metal-rich, suggesting they formed much later from gas that had already been processed through earlier stellar generations. The spread was too large, too structured, too organized to be explained away as measurement noise. Something about Omega Centauri had allowed it to form multiple generations of stars across an enormous span of time, and no standard model of globular cluster formation could account for that. The classification that had seemed settled for decades suddenly had cracks in it. Every generation of astronomers that looked at Omega Centauri thought they finally had a handle on it, and every generation eventually discovered they were only seeing part of the picture. There are roughly 200 globular clusters orbiting the Milky Way, and none of them behave the way Omega Centauri does. Start with the mass. A typical large globular cluster in our galaxy contains somewhere around a few 100,000 solar masses. Some of the more impressive ones push toward 1 million. Omega Centauri contains roughly 4 million solar masses. That is not a slight difference. That is not the kind of gap you explain away with measurement uncertainty. It is 10 times more massive than what astronomers would call a large globular cluster, and it sits so far outside the normal distribution that comparing it to its closest rivals starts to feel almost pointless. The second most massive globular cluster in the Milky Way is not even close. Then there is the shape. Globular clusters are called globular for a reason. They are spheres. Gravity pulls matter toward a common center of mass, and over billions of years the result is something that looks, from any angle, essentially round. Omega Centauri is not round. It is visibly flattened, stretched along one axis in a way that suggests rotation, and it does rotate, faster than any other known globular cluster in the galaxy. When you see a flattened, rapidly rotating stellar system, you are looking at something that has angular momentum locked into its structure. Standard globular clusters do not form that way. The dynamics that produce a rapidly spinning oblate stellar system are the dynamics of something larger and more complex than a simple cluster born from a single cloud of collapsing gas. None of that, though, is the detail that really troubles astronomers. The deepest problem with Omega Centauri is written in the chemistry of its stars. To understand why this matters, you need to know what a globular cluster is supposed to look like from the inside. The standard picture is clean. A cluster forms when an enormous cloud of gas collapses under its own gravity. In a relatively short burst, all the stars that emerge from that collapse share the same age, roughly speaking, and the same chemical composition because they all formed from the same pool of raw material. When you look at a normal globular cluster and measure the iron content of its stars, you find the same answer over and over again. Same age, same chemistry, same origin. The cluster is a single generation. One birth event, one population. Omega Centauri has at least 5. Astronomers have identified distinct stellar populations inside this cluster that differ not just in age, but in their chemical fingerprints, their helium content, their ratios of oxygen to nitrogen to sodium. The oldest stars date back roughly 12 billion years. The youngest stellar populations formed perhaps a billion or more years later. That gap in formation time is not a rounding error. It is not an artifact of imprecise measurement. It represents an extended period of star formation that continued long after the first generation of stars had already lived and died. The cluster was not just born once, it kept making stars. That is strange. That is very strange. Here is why. When the first generation of stars in a cluster grows old, the most massive among them explode as supernovae. Those explosions throw enormous quantities of gas back into the surrounding environment. In a normal globular cluster, that gas escapes. The cluster simply does not have enough gravitational pull to hold onto material ejected at supernova velocities. The gas leaves, it disperses into the surrounding galaxy. No new stars form because there is nothing left to form them from. One generation is all you get. Omega Centauri kept that gas. Something held it in, something with enough gravity to catch the material thrown off by dying stars and pull it back, compress it, and ignite new rounds of star formation. That recycled gas, now enriched with heavy elements forged inside the first generation of stars, collapsed into a second population. Then the second generation aged, and the most massive of those stars exploded, and the enriched gas from that event was retained as well. A third population formed, then a fourth, then a fifth, each successive generation inheriting a slightly more chemically complex environment than the one before it, each one carrying a chemical record of everything that came before. If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. I'd love to know where you're watching from and what time it is for you. Feel free to drop your location and time in the comments below. You cannot do that with a globular cluster's worth of gravity. The numbers do not work. Researchers have run the calculations, and a system of a few 100,000 solar masses loses its supernova ejector. It does not have a deep enough gravitational well. The gas escapes before it can collapse into new stars. To retain that material and cycle it through multiple generations of star formation, you need something substantially more massive. Something with a gravitational grip more like a galaxy than a cluster. What kind of object rotates faster than any globular cluster, carries 10 times the mass of its closest rivals, and holds onto its own stellar exhaust long enough to build entirely new populations of stars from it? What kind of system has the self-enrichment capacity to run the same process 5 times over across more than 1 billion years of continuous star formation? The answer astronomers keep arriving at is not a comfortable one for the classification of this object. It does not point toward any variant of a standard globular cluster. It points towards something else entirely, something that had, at some point in its history, the mass and structure to behave like a self-contained stellar ecosystem, rather than a simple gravitationally bound collection of stars born together and left to age quietly. An object that can hold onto its own gas through multiple stellar generations and build entirely new stars from the wreckage of the old ones is not behaving like a globular cluster at all. It is behaving like a galaxy. Every globular cluster has a chemical signature, a record of what its stars are made of, and that signature is supposed to be the same across every star in the cluster. This is not a minor footnote in stellar physics. It is a foundational principle. When a globular cluster forms, it forms all at once, from a single cloud of gas with a single chemical composition. Every star that emerges from that event carries the same proportions of hydrogen, helium, and whatever heavier elements happen to be present. Same birth, same chemistry, same age. That is the rule. Omega Centauri does not follow it. The stars inside Omega Centauri span an enormous range of chemical compositions. The most ancient members are almost pure hydrogen and helium, the original matter of the universe with barely any heavier elements at all. The youngest populations contain iron, oxygen, and other metals at concentrations many times higher. Between those extremes, there are at least 5 distinct stellar groups, each with its own chemical fingerprint, each representing a separate episode of star formation separated by hundreds of millions of years. This is not measurement noise. This is not an artifact of imprecise instruments. The spread is real, it is large, and it tells a specific story. To read that story, you have to understand what heavier elements actually mean in this context. In the early universe, almost nothing existed except hydrogen and helium. Carbon, oxygen, iron, sodium, none of those were present in significant quantities when the cosmos was young. They had to be manufactured. Stars are the factories that build them, fusing lighter nuclei into heavier ones in their cores over millions and billions of years. When a massive star reaches the end of its life and detonates as a supernova, it does not just disappear, it sprays those newly forged elements outward into the surrounding gas at tremendous velocity. That enriched gas then becomes the raw material for the next generation of stars. The second generation is chemically richer than the first. The third rich are still. In a normal globular cluster, this cycle happens once and then stops. The cluster forms its stars. Those stars produce some chemical enrichment, but the cluster's gravity is not strong enough to hold on to the gas those dying stars expel. The material escapes. There is nothing left to build a second generation from. One episode of star formation, one chemical population, end of story. What you need to sustain multiple generations is something with enough gravitational pull to trap that escaping gas, hold it, let it cool, and eventually collapse it into new stars. Normal globular clusters cannot do this. Something bigger can. Omega Centauri's oldest stars formed roughly 12 billion years ago, within about 2 billion years of the Big Bang. The universe at that point was young and metal poor, and those first-generation stars reflect that. Their iron content is at the low end of anything measured in the cluster, somewhere around a factor of 100 below what you find in the Sun. They are relics of a very different cosmos. Then those stars aged. The most massive among them burned through their fuel quickly, collapsed and exploded. Each supernova scattered oxygen, carbon, and heavier elements into the gas surrounding the cluster. Then something held that gas. Gravity pulled it back. It cooled and condensed. A second generation of stars ignited, and those stars were born already carrying the chemical legacy of everything, but had died before them. The shift between populations is not subtle. Oxygen abundances drop noticeably from the first generation to the second, because the same supernovae that enrich the gas with iron also trigger processes that consume oxygen in later stellar generations. Nitrogen rises, sodium rises, helium content climbs measurably from one group to the next, a consequence of the nuclear processing happening inside the dying stars of each prior generation. Each of these shifts is a timestamp. Each one marks a distinct era of star formation, a new wave of stellar birth following the deaths of an older wave. Astronomers can sort individual stars into their respective populations by measuring these ratios with spectrographs, reading the chemical record locked inside each star's atmosphere. The youngest populations in Omega Centauri formed perhaps 10 billion years ago, meaning the entire window of star formation stretched across something like 2 billion years. That number sounds abstract until you compare it to what happens in a standard cluster. Normal globular clusters form their stars over a period measured in millions of years, maybe tens of millions at most. 2 billion years of continuous star formation is not a cluster's timeline. That is the timeline of a galaxy building itself up through successive bursts of stellar activity, each one enriched by everything that came before. There is something almost methodical about the progression when you lay it out. Iron content rising from population to population, helium fractions climbing in a clear sequence, the changing ratios of light elements tracking the output of dying stellar generations as faithfully as a ledger. The object that produced this record was not passively sitting still while its stars aged. It was actively recycling itself, catching the debris of stellar death and spinning it into new life, generation after generation, across nearly a fifth of the current age of the universe. No globular cluster does this. A system that holds its own supernova ejector, reforms stars from enriched gas, and repeats that cycle across billions of years is not operating on a cluster's budget. The gravity required is far greater. The depth of the potential well is far steeper. The mass involved points towards something that was once much larger than what we see today. 5 generations of stars, each one forged from the ashes of the last. That is not the life story of a cluster. It is the life story of a galaxy. The Milky Way has a history of eating things. It is not a passive object drifting quietly through space. It is a large, gravitationally dominant structure that has spent billions of years pulling smaller galaxies toward it, disrupting them and absorbing their stars into its own body. Astronomers have identified several of these past mergers by tracing unusual streams of stars through the galactic halo, stars that do not belong to any known structure, moving on orbits that make no sense unless they came from somewhere else. The Milky Way has been doing this for most of its existence, and the evidence suggests it is not finished. When a small galaxy falls toward a much larger one, the process is not a clean collision, it is a slow unraveling. The outer layers of the smaller galaxy feel the gravitational pull of the larger one differently than the inner layers do. That difference, stretched over millions of years and dozens of close passes, begins pulling stars away from the smaller galaxy's edges. The outermost stars go first, then the next layer, then the next. What gets left behind, if anything survives at all, is the densest, most tightly bound region of the original galaxy, its core. That core holds together because gravity in the very center is strong enough to resist the tidal forces that dismantled everything around it. It becomes a dense, compact remnant still orbiting inside the larger galaxy that consumed it, carrying the chemical and structural memory of the system it once was. This is the leading explanation for what Omega Centauri actually is. Not a globular cluster that happened to grow unusually large, not an anomaly in the standard model of cluster formation. A galactic core, the surviving nucleus of a dwarf galaxy that fell into the Milky Way billions of years ago, had its outer stars stripped away over repeated orbital passages, and left behind only the part that gravity would not let go of. What we see today, that compressed sphere of 10 million ancient stars sitting 17,000 light-years away, is the remnant of something that was once far larger. The hypothesis does something that scientific theories are supposed to do. It explains everything at once. Go back through the list of anomalies. The mass, Omega Centauri, is 10 times heavier than the typical large globular cluster. Galaxies are heavy. A galactic nucleus would carry mass on exactly this scale. The rotation. Omega Centauri spins significantly faster than other clusters and has a visibly flattened shape as a result. Globular clusters do not typically rotate like this. Galactic nuclei do. The rotation of a galactic core is inherited from the angular momentum of the parent galaxy, and it persists even after the outer galaxy is stripped away. The shape follows directly from the rotation. The spinning system flattens along its axis. That is basic physics, and Omega Centauri's slide, but measurable oblateness, is exactly what you would predict. Then there are the stellar populations. 5 distinct generations of stars, each one chemically different from the last, spanning more than 1 billion years of star formation. Standard globular clusters cannot do this. They lack the gravity to hold onto the gas that dying first-generation stars throw off as supernovae and stellar winds. That gas escapes into the surrounding space and is gone. But a dwarf galaxy is far more massive than a globular cluster, and far more capable of retaining expelled material. When the first generation of stars in a dwarf galaxy reaches the end of its life and explodes, the gas those explosions release does not escape. It falls back, it mixes with the remaining interstellar medium, it cools, and it forms new stars. This cycle can repeat across hundreds of millions of years, generating multiple successive stellar populations with progressively richer chemistry. That is exactly what the stars of Omega Centauri are telling us. Each generation carries the chemical signature of the supernovae that came before it. Iron, oxygen, nitrogen, sodium, helium abundances all shift from the oldest population to the youngest in a pattern that maps cleanly onto a sequence of stellar birth and death and rebirth. The metallicity range fits the same picture. In a standard globular cluster, the stars have nearly identical iron abundances because they all formed from the same initial gas cloud at roughly the same time. In Omega Centauri, the iron content of individual stars spans a factor of roughly 25, from the most metal-poor to the most metal-rich. That range is a record of self-enrichment across an enormous stretch of time. It is not the record of a cluster. It is the record of a galaxy processing its own material through multiple generations of stellar evolution. Every piece lands in the right place. The mass, the rotation, the flattened shape, the multiple stellar populations, the chemical diversity, the sheer age range of the stars. All of them fit the dwarf galaxy hypothesis, and none of them fit the standard globular cluster model. Scientists call this kind of explanatory convergence compelling. When a single theory resolves a dozen separate puzzles simultaneously, and when no competing theory can account for even half of them, the argument for that theory becomes very strong. What makes the hypothesis even harder to dismiss is that it is not unique to Omega Centauri. Astronomers have found other massive chemically complex globular clusters in the Milky Way and in neighboring galaxies that show similar signatures. The process of galactic cannibalism is common enough that stripped nuclei should be relatively abundant if you know what to look for. Omega Centauri is simply the closest and most detailed example. It is the case study that made the pattern clear. There is one more implication that falls directly out of this theory. Galaxies are not just collections of stars orbiting a common center. They are organized systems with structure, and at the center of nearly every galaxy that astronomers have examined in sufficient detail, there is a massive black hole. Not sometimes, not usually, almost universally, galactic nuclei carry black holes the way stars carry cores. It is part of what a galactic nucleus is, and if Omega Centauri is the core of a devoured dwarf galaxy, then it should have the thing that sits at the center of every galaxy, a black hole. If Omega Centauri really is the stripped core of a dead galaxy, there should be a trail. When a galaxy falls into something larger, it does not disappear cleanly. The outer stars peel away first. Gravity is not uniform across a structure that large, and the side of the infalling galaxy that is closer to the Milky Way feels a stronger pull than the side that is farther away. That difference, that tidal stretching, physically tears stars loose from the outer regions and scatters them along the orbital path. What gets left behind is a long ribbon of stars spread across the sky, following the curve of the original orbit like dust left in the wake of a slow collision. Astronomers call this a tidal stream. Finding one attached to Omega Centauri would not just be interesting, it would be close to definitive. For years, the search came up empty. The stars in a tidal stream are spread so thinly across such an enormous patch of sky that picking them out from the background population of the Milky Way is genuinely difficult. They do not announce themselves. A handful of stars drifting slowly across a field of millions looks, to a casual observer, like nothing at all. The signal is there, but it is a whisper inside a crowd. Then, in 2019, Rodrigo Ibata and his team found it. Working with data from the Gaia spacecraft, which had spent years mapping the positions and velocities of more than 1 billion stars with extraordinary precision, Ibata's group identified a coherent structure of stars extending up to 18 degrees across the sky from Omega Centauri. 18 degrees is enormous. Hold your fist at arm's length against the sky. That span covers roughly 10 degrees. The Fimbulful Stream, as they named it, stretches almost twice that distance. It is not a subtle feature. It was simply invisible until the data quality was good enough to find it. The name comes from Norse mythology. Fimbulful is a river said to have existed at the beginning of the world, before time had properly started. The people who chose that name were not being careless. A stream of stars torn from a galaxy billions of years ago, still drifting through space long after the structure that produced it no longer exists. There is something appropriate about reaching for mythology to describe it. What the stream represents, physically, is the wreckage of the original disruption event. When the dwarf galaxy that became Omega Centauri first encountered the Milky Way, the outer layers were the most vulnerable. Stars in the loosely bound outer regions were the first to be pulled free. They spread along the orbital path, some moving slightly ahead of the core, some falling slightly behind, and over billions of years that spread became a detectable structure. The dense central region, the object we now call Omega Centauri, was too tightly bound to be torn apart the same way. It survived. Everything outside it did not. The mass argument matters here. Tidal streams of this scale and coherence do not form from small objects. A typical globular cluster, with its relatively modest mass, does not leave a trace, anything like this. The stream extending from Omega Centauri is the kind of structure that requires the original object to have been far more massive than a normal cluster, massive enough that when it fell in, the tidal forces acting on it were strong enough to strip enormous numbers of stars and leave a coherent trail stretching across 18 degrees of sky. The stream itself is an argument for the dwarf galaxy hypothesis, independent of everything else. But the most striking piece of this story is not the stream. It is a single star. Captain Star is a dim red dwarf sitting just 13 light-years from the Sun. By the standards of well-studied nearby stars, it is not particularly famous. It has a very high proper motion. It moves across the sky faster than almost any other nearby star, and it orbits the Milky Way on an unusual retrograde path, going the wrong direction relative to most stars in the disk. For a long time, these properties were noted and filed away without a clean explanation. The explanation, it turns out, may be Omega Centauri. The kinematics of Captain Star, its velocity, its orbit, the chemical composition of its atmosphere, are consistent with an origin inside the cluster. The current leading interpretation is that this star was stripped from Omega Centauri during one of its early close passages with the Milky Way and has been travelling through the galaxy ever since. It did not form here. It formed somewhere else, inside a structure that no longer exists as an independent object, and it has been crossing the Milky Way for billions of years. That changes the scale of this in a specific way. The Fimbulful stream is spread across a region of sky that requires a telescope and a dataset of 1 billion stars to properly see. It is real, but remote. Captain Star is 13 light-years away. Astronomers have been pointing instruments at it for well over a century. It appears in standard catalogues. Under the right conditions, a backyard telescope can find it. And it may be a refugee from a galaxy that ceased to exist in its original form before the Earth was born. A star only 13 light-years away from our Sun, close enough to appear in backyard telescope catalogues, was probably flung outward from Omega Centauri billions of years ago and has been drifting through the galaxy ever since. There is a way to read the history of a star system the same way you might read tree rings, layer by layer, oldest at the center, youngest at the edge. In Omega Centauri, that record is written in chemistry. Every star in this cluster carries a chemical fingerprint forged at the moment of its birth, and those fingerprints do not all match. They range from the nearly pristine signatures of the universe's first stellar generations to the relatively enriched compositions of stars that formed hundreds of millions of years later. That range is the evidence. It tells you without ambiguity that something very unusual happened here over a very long stretch of time. To understand why this matters, you need to know what metallicity actually means to an astronomer. The word sounds industrial. It is not. In stellar physics, metals means everything heavier than hydrogen and helium. Oxygen is a metal. Carbon is a metal. Iron is a metal. When the universe was young, none of these elements existed in any significant quantity. The Big Bang produced hydrogen, helium, and trace amounts of lithium, and that was essentially all there was. The heavier elements had to be manufactured. They were built inside the cores of massive stars through nuclear fusion, and they were scattered into the surrounding gas only when those stars died violently as supernovae. The universe had to go through at least one full cycle of stellar birth and death before it had enough heavy elements to build anything more complex than a gas cloud. The first stars that formed in the early universe were made from that nearly empty starting material, almost pure hydrogen and helium. Astronomers call these metal-poor stars, and their spectra show it clearly. The absorption lines for iron and oxygen are faint. There is almost nothing there. In a normal globular cluster, all the stars look roughly like this, because normal globular clusters formed in a single burst from a single parcel of gas that had one specific chemical composition at one specific moment in cosmic history. One burst, one chemistry, one generation. That is the standard model. Omega Centauri breaks the standard model badly. Its stars span an iron abundance from roughly -2 to -0.6 on the logarithmic scale astronomers use. That sounds like a small numerical difference. It is not. It corresponds to a factor of roughly 25 in actual iron content between the most metal-poor and most metal-rich populations inside the same cluster. 25 times more iron, in a system that was supposed to have formed all at once. That spread is not noise. It is not a measurement error. It is a record of repeated stellar generations, each one dying, seeding the surrounding gas with new elements, and giving birth to the next population. The sequence is readable if you know what to look for. The oldest stars, the ones with the lowest iron content, formed first. They lived fast, died as supernovae, and threw their heavy elements back into the gas surrounding the cluster's core. A second generation then condensed from that enriched material. Its stars carry slightly more iron, slightly more oxygen. When those stars died, they enriched the gas further still. A third generation formed, then a fourth, then what the data suggests is at least a fifth distinct population. Each generation left a chemical fingerprint slightly offset from the one before it. Astronomers can now sort individual stars in Omega Centauri into these groups based on their chemical compositions, separating them the way you might sort old coins by the year they were minted. It is not just iron that shifts across these populations. Oxygen decreases from the oldest stars to the younger ones. Sodium increases. Nitrogen increases. Helium abundances climb noticeably between the first and later generations, which actually affects how those stars look and how they evolve, making the younger helium-enhanced populations bluer and hotter than you would expect for their age. These are not subtle variations. They are systematic, consistent patterns that track across thousands of stars and paint a picture of a system undergoing extended chemical self-enrichment over hundreds of millions of years. This is why the dwarf galaxy hypothesis makes such immediate sense of the chemistry. A globular cluster does not have enough gravity to hold on to the gas expelled by dying stars. A supernova blows material outward faster than a cluster can retain it, so that gas escapes and the next generation of stars never forms inside the cluster. But a galaxy is different. A galaxy's gravitational well is deep enough to trap that ejected material, cool it, and recycle it into new stars. The chemical complexity of Omega Centauri is direct evidence that this system had the gravitational capacity to do exactly that. Something here was massive enough to hold on through multiple cycles of stellar death and rebirth. Something galactic in scale. What astronomers are doing when they analyze the spectra of individual stars in this cluster is not routine. They are doing archaeology on a cosmological scale, reading the sequence of events in a system that formed before our own sun existed. Each star is a data point in a timeline stretching back nearly 12 billion years. The oxygen ratios in one group of stars tells you what the supernovae of the previous generation contributed. The sodium enhancement in another tells you about the intermediate mass stars that shed material through stellar winds before dying quietly. Nothing is guesswork. The chemistry is a document, and it is legible. The chemical record inside Omega Centauri is not the record of a cluster, it is the record of a civilization of stars, each generation inheriting a slightly richer universe than the one before it. The stars inside Omega Centauri are old in a way that requires rethinking what old means. When astronomers say a star is old, they usually mean something like 5 or 6 billion years. Our own sun is about 4.6 billion years old, and it sits comfortably in the middle range for a star of its type. Nothing unusual, nothing that demands special attention. The stars in Omega Centauri are more than twice that age. The oldest ones formed roughly 12 billion years ago. The universe itself is 13.8 billion years old. That gap, less than 2 billion years between the Big Bang and the birth of these stars, is almost too narrow to hold in your mind comfortably. These are not old stars the way your grandparents' house is old. These are old the way the first stone tools are old. Consider what did not exist yet when these stars ignited. The Earth was not here, the Sun was not here, the solar system, the asteroid belt, every rocky planet in our neighborhood, none of it existed. The Milky Way itself was still assembling, pulling gas and smaller structures into something that would eventually resemble the galaxy we live in today. The stars now burning inside Omega Centauri were already ancient by the time the first grains of dust that would eventually become our planet had begun to gather. Here is something worth sitting with. The light reaching your eyes from Omega Centauri tonight left the cluster roughly 17,000 years ago. At that moment, humans were painting bison onto cave walls in what is now France and Spain. They had no writing, no cities, no recorded history. That light crossed 17,000 light years of empty space and arrived here, now, at your eye. And the stars that sent it are themselves 10 to 12 billion years old. The light is just the messenger. The source is incomprehensibly older. What does that age mean for the chemistry of these stars? Everything. Stars are not born equal in composition. The very first stars in the universe formed from almost nothing but hydrogen and helium because those were the only elements that existed in any quantity after the Big Bang. There was no carbon. There was almost no oxygen. Iron, calcium, silicon, the heavy elements that make up planets and eventually living things, were essentially absent. They had to be forged inside stars and scattered outward by supernovae before they could appear in the next generation of forming suns. The oldest stars in Omega Centauri formed so early that almost none of that enrichment had happened yet. Their iron content is a tiny fraction of the sun's. Their heavy element abundances are at the floor of what astronomers measure anywhere. They're the closest thing we have to the original composition of the universe, preserved in living stellar form and sitting close enough to study in detail. A star this metal poor forming today would be almost impossible to explain. Finding one 17,000 light years away, still burning, still measurable, is something else entirely. This is what makes Omega Centauri strange in a way that goes beyond scale. It is not just a lot of stars, it is a collection of stellar fossils from a cosmos that no longer exists. The universe those stars were born into looked nothing like ours. It was younger, hotter, more chaotic, and almost entirely devoid of the heavy chemistry that defines the world we know. The oldest stars in this cluster are not remnants of our universe. They are remnants of a different one. For astronomers trying to understand how the first galaxies formed, this proximity is remarkable. Early galaxy formation happened too far away and too long ago to observe directly with any current instrument. We cannot point a telescope at a galaxy 12 billion light years away and study its individual stars. We do not have the resolution, but we can study the ancient stellar populations of Omega Centauri in extraordinary detail, because they are sitting nearby. Those stars carry chemical fingerprints from the era of earliest galaxy formation frozen into their spectra. By reading those fingerprints carefully, researchers can reconstruct what the chemical environment looked like in a young galaxy before successive supernova cycles had time to build up the periodic table. What those stars reveal is a universe that was genuinely primitive. Not primitive in a dismissive sense, in a precise one. The elements needed to build planets, to build complex chemistry, to build biology, were simply not present in any significant quantity. The oldest stars of Omega Centauri formed in an environment where the universe had not yet had time to make the ingredients for worlds like ours. They are still there, still burning, unreachable but observable, ancient but visible, carrying a record of the earliest conditions that shaped everything that came after. Looking at the stars of Omega Centauri is, in a very literal sense, looking at the universe as it was before the Earth had any reason to exist. The center of Omega Centauri is not a place where stars live quietly. The average separation between stars in the core is roughly 0.1 light-years. That number sounds small in the abstract. It becomes something else entirely when you put it next to a number you know. Proxima Centauri, our Sun's nearest stellar neighbour, sits 4.25 light-years away. In the core of Omega Centauri, the average gap between any two stars is about 1/40th of that distance. If our solar neighbourhood had that kind of spacing, the nearest star to our Sun would not be a faint red dwarf 4 light-years out. It would be sitting roughly at the distance of the Oort cloud, the outermost shell of icy debris at the far edge of our solar system. That is not a neighbour. That is something sharing your driveway. At separations like these, gravity does not politely ignore the stars around it. Every star in the core is continuously feeling the pull of dozens of others, not as a distant background hum the way our Sun feels the combined gravity of the galaxy, but as a close, immediate competing tug. Stars drift through the core at a velocity dispersion of roughly 7.9 kilometers per second. That is the typical speed difference between any two stars crossing paths in the cluster's center. Fast enough that close encounters happen not once in a stellar lifetime, but repeatedly, predictably, on timescales that matter. The core of Omega Centauri is not a calm archive of ancient suns. It is a slow collision course playing out across billions of years. What happens during one of these encounters depends on how close the approach gets. A distant pass will bend trajectories, nudge orbits, scatter a star onto a slightly different path through the cluster. A closer pass can do more. Stars in binary systems can have their companions stolen by a passing interloper. A star approaching another closely enough will raise tidal distortions in its outer layers, transferring mass from one to the other, and in the densest pockets of the core, two stars can collide outright. Not in the explosive sense of two rocks smashing together. Stars are mostly gas. What happens is a prolonged, violent merger, two objects interpenetrating, their outer layers mixing, their cores eventually combining into something new, something that was not there before. This is where the environment starts producing objects that have no equivalent in quieter parts of the galaxy. Blue stragglers are one example. In a normal globular cluster, you can estimate a star's age by its colour and brightness. Stars that are very blue and very bright in a 12-billion-year-old cluster have burned through their hydrogen too fast to still be on the main sequence. They should not exist. But in Omega Centauri's core, they do. They are old stars that absorbed new fuel, either through a direct collision or by slowly siphoning hydrogen from a binary companion. The fresh hydrogen gave them a second life. They look young because in a meaningful sense they are young, rebuilt from material that was already billions of years old. They are not anomalies, they are a direct product of the environment. Millisecond pulsars are another. A pulsar is a neutron star, the collapsed remnant of a massive star after a supernova, spinning and emitting a tight beam of radiation. Normal pulsars slow down over millions of years as they radiate energy away. A millisecond pulsar spins hundreds of times per second, far faster than any isolated neutron star should. The explanation is accretion. A neutron star in a binary system pulls material from its companion. That infalling material carries angular momentum. It spins the neutron star up, like a top being whipped faster and faster until it is rotating 300 times per second. That process requires a binary companion. Dense stellar environments produce binary systems at high rates, through the same close encounters that drive everything else in the core. Omega Centauri has them in abundance. X-ray binaries follow the same logic. A compact object, a neutron star or black hole, paired with a normal companion star close enough to strip material from its outer layers. The infalling gas heats to extreme temperatures as it accelerates toward the compact object and emits X-rays. None of this happens between isolated stars. It requires proximity, repeated encounters, a neighborhood packed tightly enough that stars cannot avoid interacting with each other over long timescales. The velocity dispersion of 7.9 kilometers per second tells you something else. It tells you the core is not static. Stars are moving through it continuously, trading positions, occasionally being flung outward by a close three-body interaction, occasionally being drawn deeper inward. Over billions of years, this constant gravitational churning produces a slow net drift. Heavy objects, compact remnants, the stellar mass black holes left behind when the most massive first-generation stars died, tend to lose energy to their lighter neighbors through a process called dynamical friction. They sink. Gradually, over timescales of hundreds of millions to billions of years, the densest objects work their way toward the bottom of the gravitational potential well, the center. Whatever has been sitting at the absolute center of Omega Centauri has had 10 billion years of infalling material to draw from. Stellar remnants, disrupted binary systems, gas stripped from close encounters, entire stars captured during encounters too close to escape. The core density, the velocity dispersion, the exotic objects scattered through it, all of these are symptoms of an environment where material flows inward over cosmic time. In an environment where stellar collisions and mergers are common events stretched over billions of years, the question of what is sitting at the very bottom of all that gravity becomes uncomfortably interesting. One of the stranger consequences of packing 10 million stars into a 150 light-year sphere is that the stars start doing things to each other that they would never do in isolation. The first category of strange objects this environment produces goes by a name that sounds almost poetic: blue stragglers. In a cluster as old as Omega Centauri, you expect the most massive, hottest, bluest stars to be long dead. Massive stars burn fast. They consume their hydrogen in millions of years rather than billions, swell into giants, and explode. By now, after 10 to 12 billion years, none of them should be left. But scattered through Omega Centauri are stars that look young. They burn blue and hot. They have no business being there. What happened to them is something that could only occur in a place this crowded. Two older stars collided, or one drained hydrogen from its companion through a process called mass transfer. Either way, a depleted star received a fresh supply of fuel. It rejuvenated. It pushed itself back onto the main sequence, glowing blue as if it had just formed, while every star around it was ancient and dim. A blue straggler is essentially a star that cheated. It absorbed someone else's future. In a less crowded environment, those two stars would never have met. They would have aged and faded separately, unremarkably. Omega Centauri brought them close enough to interact, and the result is an object that should not exist given the age of its surroundings. Then there are the millisecond pulsars. A pulsar is a neutron star, the collapsed remnant left behind when a massive star explodes. Neutron stars are extraordinarily dense. A single teaspoon of neutron star material would weigh roughly 1 billion tons. When they form, they spin. Most slow down over time as they radiate energy away into space. A millisecond pulsar, though, spins hundreds of times per second. Some complete more than 700 rotations every second. That rotation rate is not something a neutron star achieves on its own. It requires a donor. In a binary system, a neutron star can pull material from a companion star. As that material spirals inward and falls onto the neutron star's surface, it carries angular momentum with it. The neutron star spins faster. Over millions of years of accretion, the spin rate climbs to extraordinary values. What you end up with is a neutron star rotating so fast that its surface is moving at a significant fraction of the speed of light. Omega Centauri's dense environment is precisely the kind of place where binary systems form, disrupt, and reform through repeated stellar encounters. The cluster is an accelerator for this kind of interaction. X-ray binaries follow a similar logic. These are systems where a compact object, either a neutron star or a black hole, is stripping gas from a companion. The gas does not fall straight in. It forms a disk, spiraling inward and compressing, heating to temperatures of millions of degrees. At those temperatures, the gas glows not in visible light, but in X-rays. From Earth, these systems appear as point sources of high-energy radiation sitting inside the cluster. They are violent places. The compact object is slowly consuming its companion. The companion is losing mass faster than it can replace it. The whole system will eventually exhaust its supply of transferable material and go quiet. But while it lasts, it blazes in X-rays against the cooler background of the surrounding stars. The numb R of X-ray binaries per unit of stellar mass in Omega Centauri is far higher than in the field. That is not a coincidence. It is a direct product of the encounter rate inside the cluster. Variable stars tell a different kind of story. Omega Centauri contains a large population of RR Lyrae stars and Type II Cepheids, both of which pulsate with periods that are tightly linked to their intrinsic luminosity. This relationship, the period-luminosity relation, makes them extraordinarily useful. If you measure how long the pulsation cycle takes, you know how intrinsically bright the star is. If you know how intrinsically bright it is and how bright it appears from Earth, you can calculate the distance with precision. RR Lyrae stars in Omega Centauri have been used as distance anchors for over a century. They helped pin down the cluster's distance at roughly 17,000 light-years and cross-checked measurements from other methods. These stars are not products of the cluster's density in the same way that blue stragglers or millisecond pulsars are, but their presence in large numbers gives astronomers a reliable ruler embedded inside the object they are trying to measure. The cluster essentially comes with its own calibration tools. What connects all of these objects is the environment that produced them. Blue stragglers, millisecond pulsars, X-ray binaries, none of these form efficiently in regions where stars are spread thin. They require close encounters, mass transfer, collisions, binary disruptions and captures. Those events happen rarely when stars are separated by light years. They happen routinely when stars are separated by a fraction of a light year, as they are inside Omega Centauri's core. The cluster is not just a collection of stars aging together. It is an environment where stellar evolution gets forced into pathways that simply do not exist under normal conditions. Stars that should have died billions of years ago are still burning. Neutron stars that should have spun down are still whirling. Compact objects that should be dark are still feeding. The physics here operates under pressure that most of the galaxy never experiences. Every one of these exotic objects is a record of what happens when stellar physics gets pushed past its normal operating conditions. And the most extreme product of all that compression sits at the cluster's very center. For more than a decade, the argument about whether Omega Centauri has a black hole at its center was the kind of disagreement that makes astronomers uncomfortable at conferences. Not because the science was sloppy, because the science was genuinely hard, and both sides had defensible positions, and the data kept refusing to settle things cleanly. To understand why the argument lasted as long as it did, you need to understand what kind of object astronomers were actually looking for. Black holes come in a rough hierarchy of sizes. At the bottom are stellar mass black holes, the remnants of the most massive stars, typically ranging from a few solar masses up to perhaps 100. At the top are the supermassive black holes that anchor the centers of large galaxies, running from millions to billions of solar masses. The one sitting at the center of our own Milky Way weighs in at about 4.3 million solar masses. Between those two extremes, there is a range that, for a long time, had almost no confirmed occupants. Objects in the range of hundreds to tens of thousands of solar masses, intermediate mass black holes, the missing link in E family. Theorists had predicted they should exist. The logic was straightforward. If stellar mass black holes form from dying stars, and supermassive black holes grow at the centers of galaxies over billions of years, then something must occupy the territory in between. Either supermassive black holes grew from intermediate seeds, or they did not, and either way that middle category should be findable somewhere. But finding them turned out to be far harder than predicting them. They are too small to show the dramatic effects that supermassive black holes produce, the bright accretion disks, the relativistic jets, and too large to form from a single stellar death. They were theoretically expected and observationally elusive. Omega Centauri, given everything that was known about it, seemed like a reasonable place to look. If it really was the stripped core of a dwarf galaxy, then the original galaxy almost certainly had a central black hole of its own. Dwarf galaxies have central black holes. That is just what galactic nuclei do. Whatever the original galaxy's black hole weighed before the Milky Way disrupted the system, it should still be sitting somewhere in the dense center of what remains. Stripped of the surrounding galaxy, it would not have grown much since the merger. It would be sitting there, quiet and dark, somewhere in the mass range that astronomers have been trying to confirm for decades. The second reason to suspect a black hole was the stars themselves. When astronomers looked carefully at how stars were moving in the innermost region of Omega Centauri, something was off. The stars near the center were moving faster than they should have been. In a system held together purely by the gravity of visible stars, you can calculate expected velocities. The math is not complicated. You add up the masses, you model the distribution, and you get a prediction. The prediction was not matching the observations. Something invisible was contributing to the gravitational pull at the center, something with significant mass that the telescopes could not see directly. This is where the argument started. Velocity measurements in the dense core of a globular cluster are not simple to obtain. The core of Omega Centauri, from Earth, is a region of sky packed so tightly with stars that separating the light of individual stars from the blended glow of their neighbors requires exceptional resolution. Ground-based telescopes, even on the best nights at the best sites, struggled to isolate clean velocity measurements for individual stars close to the center. Spectroscopic observations of stars at the cluster's heart were contaminated by light from surrounding neighbors. The measurements had error bars large enough to matter. Different research teams attacked the problem with different instruments and different methods. Some groups reported velocity dispersions in the core that pointed clearly to a central mass concentration of roughly 40,000 solar masses. Others analysed similar data and concluded the elevated velocities could be explained by a dense cluster of stellar remnants, white dwarfs, neutron stars, stellar mass black holes, concentrated at the centre through dynamical friction, with no single massive object required. The same signal, two interpretations, neither side could definitively rule out the other. That ambiguity persisted for years. Papers appeared pointing toward a central black hole. Counterpapers appeared arguing against it. Some analyses put the mass of the hypothetical black hole at 40,000 solar masses. Others revised it downward. One study suggested it might be as small as 8,000 solar masses, if it existed at all. There was a strange quality to the debate, a signal that was almost too clean to dismiss, and yet too uncertain to confirm. It reminded some researchers of the early arguments over the Milky Way's own central black hole, before the long baseline of stellar orbit measurements finally made the case undeniable. The core of the problem was resolution, not conceptual resolution, physical resolution. The angular size of the innermost region of Omega Centauri, as seen from Earth, is tiny. Measuring the true velocity of a star in that region requires separating its light cleanly from the light of stars only fractions of an arcsecond away. Ground-based instruments could not do it reliably. Space-based instruments could, but the data they produced needed time to accumulate. A single snapshot of a star's position does not tell you how fast it is moving. You need multiple observations separated by years, sometimes decades, to measure proper motion. The slow drift of a star across the sky as it orbits the cluster's center. What finally broke the stalemate was not a new instrument, it was time, and the patience to accumulate enough of it. More than 500 images taken over 2 decades, each one showing a cluster of 10 million stars, and what the researchers were looking for was the movement of 7 of them. The team came from the University of Utah and the Max Planck Institute for Astronomy. They had access to Hubble data stretching back to the early 2000s, hundreds of observations of the same crowded patch of sky, each one recording the precise positions of stars in the innermost region of Omega Centauri. What they were doing, in principle, is straightforward. If you photograph the same star field twice, separated by enough time, you can measure how far each star has moved across the sky. That movement is called proper motion. For stars as distant as Omega Centauri, the actual displacement per year is extraordinarily small. We are talking about fractions of a pixel on a detector that is already resolving one of the most densely packed stellar environments in the galaxy. A single image tells you almost nothing. 2 images tell you a little more, but stack hundreds of them, spanning 2 full decades, and suddenly the noise falls away and the signal becomes readable. The core of Omega Centauri is not easy to work with. Stars in its central region are so tightly packed that even Hubble, at its resolution, sees them blending into each other at certain wavelengths. Separating individual stellar positions with enough precision to track motion at the level of milliarcseconds per year requires careful image processing, careful calibration, and a dataset large enough to average over every source of error. This is why it took 2 decades, not because the black hole was waiting to be discovered, but because the measurement required time itself as an instrument. When the researchers mapped out the velocities of stars across the inner region, most of them behaved as expected. Stars in a gravitationally bound system move in predictable ways. The cluster's visible mass, roughly 4 million solar masses distributed across 10 million stars, produces a gravitational field that you can model, and that model makes predictions about how fast stars at any given distance from the center should be moving. For the vast majority of stars in the dataset, the observations matched the model. Then there were 7 that did not. 7 stars, all in the innermost region of the cluster, were moving significantly faster than the surrounding population. Not slightly faster, not within the margins of measurement uncertainty. They were moving at speeds that the gravitational field of the visible stars alone simply could not produce. Something else was pulling on them, something concentrated, something massive, and something that was not showing up in any image. This is the velocity signature of a hidden massive object. When a star passes close to something extremely dense, it gets accelerated. The closer the pass, the greater the acceleration. If you map the velocities of many stars in the vicinity of the hidden object, the pattern that emerges is distinctive. Stars near the center move faster than stars farther out, more than the visible mass alone would predict, and the excess velocity increases as you get closer to the center. That is exactly what the 7 fast-moving stars were showing. They had been slingshot by something sitting at the core. The analysis put the mass of that hidden object at a minimum of 8,200 solar masses. 8,200 times the mass of our Sun, packed into a region too compact to be a cluster of smaller objects. The researchers described it as the first intermediate mass black hole reliably observed to date. That word reliably matters. Previous candidates had existed. Previous studies of Omega Centauri and other dense clusters had produced hints, contested measurements, alternative explanations. None of them had held up cleanly under scrutiny. This one did. To understand why this is significant, you need to hold the black hole mass spectrum in your mind. Stellar mass black holes form when massive stars die. They weigh between a few and perhaps 100 solar masses. Supermassive black holes anchor the centers of galaxies and weigh millions to billions of solar masses. The gap between those two categories, from roughly 100 to a few million solar masses, was theoretically expected to be populated by intermediate mass black holes, but finding one had proved frustratingly difficult. They are too massive to form from a single dying star, and too small to detect with the indirect methods used on galactic centers. For decades, they were the missing link in the black hole family, predicted by theory, hinted at by data, confirmed by nothing. Ig, each 1,200 solar masses sits firmly in that gap. This was the object that had been missing from the picture. There is a second layer to what this discovery confirmed. The dwarf galaxy hypothesis, built over decades from multiple independent lines of evidence, had always carried one implication that could not yet be tested. Every galaxy has a black hole at its center. Not most galaxies. Every one with enough mass to qualify. If Omega Centauri really is the surviving core of a swallowed dwarf galaxy, then it should have a black hole. The velocity data from those 7 stars said that it does. The two conclusions arrived together, each one reinforcing the other. The black hole is real, and its existence at the center of Omega Centauri is exactly what you would expect to find in the nucleus of a disrupted galaxy, not in a globular cluster born from a single burst of star formation in the Milky Way's halo. The paper drawing these conclusions was described by researchers in the field as the most compelling evidence yet assembled for an intermediate mass black hole in any system. It closed a debate that had stretched across more than a decade of conferences, competing analyses, and inconclusive results. One discovery, 2 confirmations. A black hole in the size range astronomers had been searching for since the 1990s, and proof that Omega Centauri is what many had suspected. The surviving core of a galaxy the Milky Way swallowed long ago. The intermediate mass black hole at the center of Omega Centauri is probably not the only black hole in there. When the Hubble team confirmed that 8,200 solar mass object sitting at the cluster's core, it answered one question and immediately raised another. If Omega Centauri is the surviving core of a devoured dwarf galaxy, then it has spent the last 10 billion years doing what dense stellar environments do, burning through massive stars, collapsing them, leaving behind compact remnants. The most massive stars in any stellar population live fast and die violently. They exhaust their fuel in millions of years rather than billions, collapse inward. In many cases, leave behind stellar mass black holes. Omega Centauri had 10 million stars to start with. A significant fraction of the heaviest ones are already gone. What replaced them did not disappear. It just became invisible. Current theoretical models predict that Omega Centauri should contain somewhere around 10,000 stellar mass black holes at this point in its evolution. That number is staggering on its own, but consider what it means structurally. These are not objects sitting still. In a dense stellar system, compact remnants like black holes move differently from ordinary stars. They are heavier than the average object in the cluster. In a gravitationally bound system, heavier objects tend to lose energy to lighter ones through repeated gravitational encounters and gradually sink toward the center. Astronomers call this process dynamical friction. It is slow. It operates on timescales of hundreds of millions to billions of years. But Omega Centauri is old enough for it to matter. The black holes that formed early in the cluster's history have had enormous spans of time to migrate inward. The ones that sank deepest are now contributing to the central mass concentration that surrounds the intermediate mass black hole at the core. For a long time, this population of stellar mass black holes was entirely theoretical. The core of Omega Centauri is so crowded, so bright with overlapping starlight, that picking out the subtle gravitational signature of an individual black hole hidden inside that environment was effectively impossible. Then, In 2026, a team of researchers managed to pull one of them out of the noise. The object they identified is designated Omega Cat BH2. It was not detected directly. Black holes rarely are. It was found the same way most of them are found, through the motion of something orbiting it. A companion star circling this invisible mass gave it away. The companion's path through space carried the signature of something much heavier, pulling on it from close range. When the researchers worked out the orbital parameters, the numbers were striking. The companion star takes approximately 94 years to complete a single orbit around Omega Cap BH2. That is the longest orbital period ever recorded for a confirmed black hole and star binary system. The star is moving slowly around something it cannot escape, on a path so wide that no human alive today will live to watch it complete a full loop. The mass of Omega Cat BH2 came out at roughly 4.46 times the mass of the Sun. That puts it squarely in the category of stellar remnants, the kind of object left behind when a massive star runs out of fuel and collapses. It is not exotic in terms of its size. Stellar mass black holes in this range are common enough elsewhere in the galaxy. What makes this one remarkable is where it was found, and what finding it implies. Omega Centauri has been a theoretical black hole reservoir for years. This detection is the first time an individual object from that reservoir has been identified and characterized. It confirms that the reservoir is real, and if one has been found, the logic pushes forward hard. Detecting this one required years of patient observation and careful analysis of a star's subtle motion. The cluster contains roughly 10 million stars. The fraction of those that have been watched closely enough and long enough to reveal an orbiting black hole is very small. The 10,000 predicted objects are not uniformly distributed through the cluster either. Dynamical friction concentrates them toward the center, where the stellar crowding is at its worst and where individual measurements are hardest to make. The 10,000 figure is almost certainly closer to a lower bound than a ceiling. What this creates, when you step back and look at the full picture, is a hierarchy of dark objects stacked inside this ancient system. At the base of the hierarchy sits the 8,200 solar mass intermediate mass black hole, confirmed by the motions of 7 fast-moving stars in the innermost region. Surrounding it, at various distances, are thousands of stellar mass remnants slowly migrating inward through dynamical friction. Each one the collapsed core of a first-generation star that burned out billions of years ago. The cluster we observe in visible light, the 10 million glowing suns, the blue stragglers. The red giants is the luminous surface of something far denser and darker underneath. This is not a static picture. The black holes keep sinking. Material keeps falling inward. The central concentration of dark mass grows incrementally over cosmic time. What began as a dense galactic core 10 or 12 billion years ago has had the entire age of the universe to compact itself further. That process is still running. 10,000 invisible masses, remnants of stars that burned out before the Earth formed, slowly sinking toward the center of the cluster over billions of years. The intermediate mass black hole at the bottom is just the end point of a very long journey. You might expect that a place with 10 million suns would be the most likely address in the galaxy for complex life. More stars means more chances. More chances means more worlds. The logic seems almost self-evident. It is also almost certainly wrong. The problem starts with distance, or rather, the lack of it. In the core of Omega Centauri, the average gap between neighboring stars is roughly 0.1 light-years. That number needs a comparison to land properly. The nearest star to our Sun is Proxima Centauri, sitting 4.25 light-years away. In Omega Centauri's core, the equivalent of our nearest neighbor would be 13 times closer. Not slightly closer, 13 times. A star that, in our neighborhood, would be an unremarkable point of light in the distant sky, would instead be a blazing, gravitationally significant presence looming at a fraction of that distance. And there would not be one such neighbor. There would be thousands. Here is what that means for planets. Every star commands a region of space where its gravity dominates, where objects orbit it predictably, where a planet can complete stable loops year after year, century after century. Astronomers call this the sphere of gravitational influence. The size of that sphere depends on how close the next massive object is. Pack stars together tightly enough, and those spheres shrink to almost nothing. A passing star does not have to actually collide with a solar system to destroy it. It just has to come close enough to tug, to perturb, to nudge a planetary orbit slightly off course. One such encounter might change very little, but in the core of Omega Centauri, these encounters happen repeatedly, on timescales of millions of years, stacking disturbance upon disturbance. Over the age of the cluster, no planet in the core could survive that. The orbits would be scrambled, planets would be flung inward toward their stars, or outward into the cold or stripped away entirely. Stable, habitable worlds require billions of years of gravitational quiet. The core of this cluster offers none. Then there is the light. Earth receives radiation from one star. In the core of Omega Centauri, the ambient starlight from the surrounding stellar population would make the sky roughly 100 times brighter than ours, even setting aside whatever nearby star a hypothetical planet happened to orbit. That is not just a visual curiosity. It represents an enormous radiation load. Ultraviolet flux, X-rays from the cluster's population of X-ray binaries and millisecond pulsars. The electromagnetic environment in the core is brutal. Shielding that would protect surface life on a planet like Earth would be insufficient. The cluster does not just make planetary orbits unstable, it also floods any surviving surfaces with far more energy than most biochemistry could tolerate. There is also the chemistry problem, particularly for the oldest stars. The earliest generation of stars in Omega Centauri formed roughly 12 billion years ago, when the universe had barely produced any heavy elements at all. Iron, silicon, magnesium, the raw materials of rocky planets, were genuinely scarce. A star forming from metal-poor gas in the early history of this cluster would have had very little to build planets from. The terrestrial worlds that formed around first-generation stars in Omega Centauri, if any formed at all, would have been thin, metal-depleted, barely rocky. The Earth is a product of a star that formed in a relatively enriched galaxy. Nothing equivalent existed in this cluster 12 billion years ago. Some researchers have pushed back against the simplest version of this conclusion. The core is extreme, but Omega Centauri is 150 light-years across, and the outer regions of the cluster are considerably less dense. Stellar separations there are larger. Gravitational encounters are less frequent. A handful of studies have argued that stable orbits might be possible in the lower density zones toward the cluster's edge, where conditions are merely unusual rather than catastrophically hostile. The later generations of stars, somewhat more metal-rich, could in principle have produced planets with more solid material. This is a minority view, and it does not overturn the overall picture, but it is a real scientific argument rather than a wishful one. The dominant assessment, though, is not optimistic. Dynamical modelling consistently shows that even in the outer regions of the cluster, the encounter rate over billions of years is high enough to destabilize most planetary systems before life could establish itself. The radiation environment extends well beyond the core. The time required for complex life to develop, something on the order of several billion years of relative stability, simply does not appear to be available anywhere inside this object. For all its extraordinary mass and density, Omega Centauri is probably one of the least hospitable environments in the galaxy for anything resembling biology. That is the strange irony at the heart of this object. 10 million stars, some of the oldest suns in the universe. An environment so rich in energy and matter that it has been forming and destroying stars for 12 billion years. All those stars, and in all likelihood, not a single one of them illuminates a world where anything is looking back. Every 120 million years, Omega Centauri plunges through the flat disk of the Milky Way, and every time it does, the galaxy takes something from it. The force responsible is the same one that pulls ocean water toward the moon: tidal gravity. The principle is straightforward. When a large mass sits close to a smaller one, the gravitational pull it exerts is not uniform. The near side of the smaller object gets pulled harder than the far side. That difference in pull across the object's width is what creates a tidal force, and for something like Omega Centauri passing through the dense stellar and gas disk of the Milky Way, the difference is not subtle. The cluster's outer stars, the ones sitting at the edges of its gravitational reach, feel a net force pointing away from the cluster's center. If that force exceeds the cluster's own gravity at that distance, the stars simply leave. They do not explode outward dramatically, they drift. Over thousands of years, they detach from the cluster and settle into orbits of their own around the Milky Way, scattered through the galactic halo like breadcrumbs, trailing behind a traveler. This process has been running for billions of years. Every 120 million years, another passage. Another round of stripping. The outer layers go first, then the next layer, then the one beneath that. What remains is always the deepest, most tightly bound material. The stars sitting so far down inside the cluster's gravitational potential well that even the Milky Way's tidal reach cannot dislodge them. The cluster we observe today is not what existed at the beginning. It is the residue, the core of something vastly larger, pared down passage by passage over an immense span of time. If Omega Centauri really was once the nucleus of a dwarf galaxy, the original structure surrounding it was enormous by comparison. Dwarf galaxies can span thousands of light years. Their outer stellar populations are loosely bound, thin, and spread across enormous volumes of space. When the Milky Way began disrupting that parent galaxy billions of years ago, the outer stars were the first to go. They were stripped away almost immediately on cosmic timescales, scattered into the Milky Way's halo where they still drift today. What was left was progressively smaller and denser with each interaction. The outer disk of the dwarf galaxy vanished first, then the intermediate regions, then the looser halo stars surrounding the core itself. What the Milky Way could not easily reach was the nucleus, dense, massive, gravitationally stubborn. That nucleus is Omega Centauri. The evidence for this erosion is written across the sky. In 2019, astronomers identified a tidal stream extending up to 18 degrees from Omega Centauri, a river of stars flung outward during past passages through the galactic disk and stretched along the cluster's orbital path. They named it the Fimbleful Stream. It is not a tight, coherent structure. It is a faint, diffuse trail of individual stars spread across an enormous arc of sky, each one following a slightly different orbit from its neighbors. Detecting it required careful subtraction of everything else in the field, pulling out a whisper of signal from a crowded background. But it is there, 18 degrees of sky, traced in the positions and velocities of stars that used to belong to Omega Centauri and no longer do. The stripping has not stopped. Omega Centauri is still on its orbit. It still punches through the galactic disk on a cycle measured in hundreds of millions of years. Each passage is another opportunity for the Milky Way to reach in and take more. The rate of mass loss depends on the cluster's mass and how deeply it penetrates into the disk. At its current mass, models suggest it will continue shedding stars for billions of years before the process finally resolves into something much smaller and more compact than what we see today. There is something strange about looking at Omega Centauri with this in mind. The 150 light-year sphere of 10 million stars that we call a cluster and study as though it is a static object is actually moving, losing stars on every orbit, shrinking on timescales too slow to observe directly, but too large to ignore over geological time. The stars visible in the cluster tonight are the survivors of a selection process that has been running for roughly 10 billion years. Every star that was not bound tightly enough is gone. The ones that remain are the ones that fell deep enough into the gravitational center to hold on. The thimbleful stream is those missing stars, still trailing behind the cluster like a wake, marking the path of something that used to be much larger. Individual stars in that stream have been travelling their own orbits for so long that they are no longer spatially close to Omega Centauri at all. They are spread across thousands of light years of the Milky Way's halo, anonymous and unremarkable, with no outward sign that they were ever part of something else. One of them, Captain's Star, ended up only 13 light years from our own sun, a refugee from the original disruption, drifting through the local stellar neighborhood for billions of years. The Milky Way has been patiently dismantling Omega Centauri for billions of years, one passage at a time, and what we call the cluster today is just the part it has not yet managed to pull away. Omega Centauri is not just an interesting object in its own right, it is a window into how the Milky Way became the galaxy it is. The Milky Way did not arrive at its current shape through some orderly, self-contained process. It grew the way most large galaxies grow, by consuming smaller ones. Dwarf galaxies fell into its gravitational reach, got torn apart by tidal forces, and their stars were scattered into the halo or folded into the disk, their gas-fueled new star formation. Their dark matter merged into the larger structure. This is not a dramatic event that happened once and finished. It is an ongoing process, spread across billions of years, still producing measurable effects in our galaxy's structure today. The stellar halo above and below the Milky Way's disk is largely made of stars from disrupted systems. The chemical gradients you find across different populations of old stars carry the signatures of those ancient mergers. The galaxy we live in is, in a meaningful sense, built from the wreckage of smaller ones. What makes Omega Centauri remarkable in this context is that it is not a wreck, it survived. While the dwarf galaxy that once surrounded it was stripped away passage by passage over billions of years, the dense core held together. It was massive enough and compact enough to resist the tidal forces that dismantled everything around it. The result is something extraordinary, an intact remnant of a merger event sitting only 17,000 light-years away, close enough to resolve individual stars with the right telescope. Most of the evidence for galactic mergers comes from statistical studies of stellar streams and halo populations. Omega Centauri is different. It is the actual core, preserved, observable in extraordinary detail. That changes what you can learn from it. Every anomaly that sets Omega Centauri apart from standard globular clusters turns into a data point when you study it as a galactic remnant. The 5 distinct stellar populations are not a mystery anymore. They are a record of extended star formation inside a system with enough mass and gravity to keep enriching its own gas supply. The chemical range from the most metal-poor ancient stars to the relatively metal-rich later generations mirrors exactly the kind of self-enrichment you see in dwarf galaxies, not in clusters. The fast rotation and flattened shape are what you expect from a galactic nucleus, not from a system that condensed as a single gravitationally bound ball. The intermediate mass black hole fits naturally at the center of something that was once a galaxy's core. None of these features make sense in isolation. Together they build a consistent picture of what Omega Centauri actually is, and where it came from. The black hole finding carries implications that extend well beyond Omega Centauri itself. For years, intermediate mass black holes occupied an uncomfortable gap in the black hole mass spectrum. Stellar mass black holes, the remnants of collapsing massive stars, were well documented. Supermassive black holes at the centers of large galaxies were established, but the intermediate range, spanning 10,000 to 100,000 solar masses, was poorly evidenced. Theory said these objects should exist. Models of galaxy formation predicted them, but reliable detections were almost non-existent. Omega Centauri, with its confirmed black hole of at least 8,200 solar masses, is the clearest example yet found. And if the reasoning is right, that this cluster is a stripped dwarf galaxy core, then it follows that other stripped dwarf galaxy cores should harbour similar objects. The Milky Way has consumed multiple dwarf galaxies. Other large galaxies have done the same. The catalogue of candidate systems that might contain intermediate mass black holes just became longer and more specific. Astronomers now have a template. The tidal stream adds another dimension. The Fimbulful stream stretching 18 degrees across the sky is not just evidence for Omega Centauri's galactic origin. It is a fossil record of the merger event itself. Stars ripped away during that original encounter have been drifting through the halo for billions of years, tracing the path the original system travelled as the Milky Way pulled it in. Reading the stream's properties, its length, its stellar content, its kinematics, gives astronomers a way to reconstruct conditions at the time of the merger and constrain models of how that interaction unfolded. Captain's star, a dim red object sitting just 13 light-years from our own sun, is believed to be one of those refugees, a relic from that ancient system, drifting through the local neighbourhood for billions of years, close enough to observe in amateur catalogues. The merger left traces at almost every scale you care to measure. What Omega Centauri offers, ultimately, is a chance to study galactic evolution from the inside out. The chemical record encoded in its stellar populations maps onto the broader story of how early galaxies built up their heavy element inventories over the first few billion years of cosmic history. The dynamics of its core test models of how black holes grow in dense environments. Its orbit and tidal features constrain models of how the Milky Way assembled its halo. Each of these questions has implications that reach far beyond this single object. The answers inform how we model galaxy formation across the observable universe. Every time astronomers study Omega Centauri in detail, they are not just studying a cluster, they are reading a chapter of the Milky Way's own biography that would otherwise be invisible. Step back from the black holes and the stellar populations and the tidal streams, and consider what this object actually is from the distance of human experience. There is a smudge of light in the southern sky that has been there since before anyone was recording history. Civilizations rose and collapsed beneath it. Navigators crossing the Southern Ocean used it as a fixed point in the dark. Ptolemy catalogued it around 150 AD and wrote it down as a star on the centaur's back because that is all he could see. A single point, a soft blur in the darkness that did not quite behave like the stars around it. For roughly 1,500 years after that, no one looked hard enough to know any better. The object sat in the sky, patiently carrying its secrets, while every generation of humans beneath it moved through their entire lives without any idea what they were actually looking at. This is what makes Omega Centauri strange in a way that goes beyond the physics. The strangeness is not just that it contains 10 million stars, or an intermediate mass black hole, or 5 distinct generations of stellar populations spanning a billion years. The strangeness is that it has been sitting there, visible, the whole time, not hidden behind clouds of dust, not tucked into a region of sky inaccessible to the naked eye. Right there, apparent magnitude 3.9. Bright enough that anyone in the southern hemisphere on a clear night could raise a hand, find Centaurus, and point directly at it. And for nearly all of human history, no one had any idea it was the preserved core of a dead galaxy. James Dunlop looked at it in 1826 and saw it resolved for the first time into individual stars. A beautiful globe of stars, he wrote, very gradually and moderately compressed to the centre. That description was a genuine breakthrough. For the first time, someone understood it was not a smear of gas, but an actual collection of individual suns. Dunlop thought the problem was solved. It was not. A century later, astronomers found that its stars had wildly different chemical compositions which standard cluster models could not explain. They thought that was the deepest layer. It was not. Decades after that, researchers identified multiple distinct stellar populations. Then came the rotation anomaly, the flattened shape, the extended tidal stream, the dwarf galaxy hypothesis. Each generation of astronomers arrived at Omega Centauri confident they had finally closed the file and each generation discovered a new door they had not seen before. The tidal stream was not found until 2019. 2 decades of Hubble observations were required to detect the 7 fast-moving stars that confirmed the intermediate mass black hole. The stellar mass black hole designated Omega Cat BH2 was identified in 2026. These are not old discoveries. The object has been in the sky for 10 billion years, and humans have been naming constellations for at least 3,000 of them, and we are still finding fundamental things about it right now. There is something almost uncomfortable about that timeline. It implies that the sky we think we understand is not the sky that actually exists. The familiar objects are not fully mapped. They are not finished subjects. Omega Centauri did not change between Ptolemy and now. The black hole was always there. The 5 stellar populations were always there. The Fimbulful stream was always stretching 18 degrees across the sky, scattered remnants of the original galaxy that became this object. Nothing was hidden in the sense of being concealed. It was hidden in the sense that the tools required to see it had not been invented yet, and in some cases had barely been invented now. The oldest stars inside Omega Centauri formed roughly 12 billion years ago, within 2 billion years of the Big Bang. The universe at that point was a very different place. Essentially no heavy elements existed outside of the lightest gases. The first stellar generations had to forge everything heavier than helium in their own cores and scatter it outward when they died. Those early stars are still in there. Their light is crossing 17,000 light-years of space right now to reach any set of eyes pointed at the right patch of southern sky. You are not looking at history in the way you look at a photograph. You are receiving signal from it directly, photons that have been traveling since before the Earth existed, landing on a retina that evolved billions of years after they were emitted. And still the object keeps yielding new things. More black holes almost certainly remain undetected inside it. The full structure of the tidal stream has not been completely mapped. The question of exactly how many distinct stellar populations are present, and precisely how they relate to one another in age and chemistry, has not been fully resolved. The intermediate mass black hole confirmation came only after more than 20 years of accumulated images, which means there are probably things inside Omega Centauri that require 20 more years of data we have not yet collected. The smudge of light above the southern horizon has been there your whole life, and the whole life of every person who ever lived, and it turns out to be a dead galaxy's core, carrying 10 million ancient suns, and a black hole, and a trail of stolen stars stretching across 18 degrees of sky, and we are only now beginning to read what it says.